Hey, what's up, guys? Jepril here, back at it again with another video. So, first off, shoutouts to my prop for making me do this. And second off, if you subscribe to my channel, you might actually get another chapter 10 because I might end up repeating this course. Now, to start things off, let's first have the easiest question, which is problem 10.9 from page 353. The flywheel of an engine has a moment inertia of 2.0 kg meter squared about its rotation axis. What constant torque is required to bring it up to an angular speed of 450 rev per minute in 7.9 seconds starting from rest? So the first thing you need to understand here is, before starting a problem, you need to convert all units into standard units, which means that angular speed needs to be in rad per second. And everyone knows that 1 rev is equals to 2 pi rad and 1 minute is equal to 60 seconds. And all that said, let's move on to the given. Your given time, which is 7.9 seconds, your given moment inertia, which is 2.0 kilogram meter squared, and you're giving angular speed, which is 450 rev per minute, which, when you divide it and turn it to seconds, is 7.5 rev per second, and if you multiply it by 2 pi to make it rad per second, it becomes 47.12. So all you have to do is find the angular acceleration and the torque. Now, first off, torque is equals to moment of inertia times acceleration, while velocity is equals to velocity initial plus angular acceleration times time. So first off, you don't have an initial angular velocity because it started from rest. So that means that angular velocity is equals to simply acceleration times time. You're given the final angular velocity or the angular velocity at that moment. So just plug it in. 47.10 rad per second is equals to 7.9 a. So just divide both sides by 7.9 and you get the final answer, which is 5.96 rad per second squared. Plug that in to get torque and you get 2 times 5.96, which is simply 11.9 newtons per meter. Newton times meter. Now let's move on to a more complex problem. So from 10.23 from page 354, a 386 Newton wheel comes off a moving truck and rolls without slipping along a highway. At the bottom of the hill, it is rotating at 27.1 rad per second. The radius of the wheel is 0.632 meters and its moment of inertia about its rotation of axis is 0.8 mr squared. Friction does work on the wheel as it rolls up to the hill first to a stop. A height h above the bottom of the hill. This work has an absolute value of 3,506 joules. Calculate h. So first off, work done by friction is an absolute value of 3,506 joules. The reason why they had to specify that it's an absolute value because friction always does negative work, because friction always slows down an object until it goes to a stop. The only time that it doesn't is when friction doesn't exist, and that only happens when it's on a slippery or in an icy plane. Now, the given here is your given weight, which is 386 newtons. To find mass, all you have to do is derive it from mass times gravity is equals to weight. So just divide both sides by gravity and you get weight is equals to mass is equals to weight over gravity, which means that mass is simply 39.38 kilograms. Now, angular velocity is 27.1 rad per second. The equation for angular velocity is linear velocity over radius. So the equation for velocity is simply angular velocity times radius, which is 17.12 meters per second. Now, the radius is equals to 0.632 meters, and the moment inertia is equals to 0.8 mr squared, in which if you plug in the m, which is 39.38 times r, which is 0.632 squared, you get a value of 12.51 kilogram meter squared. And the absolute work done by friction is 3,506 joules. Now, to start things off, work total is equals to change in kinetic energy minus work done by friction. Now, that's equal to 1 half IW squared final minus 1 half IW squared initial plus 1 half MV squared final minus 1 half MV squared initial minus work done by friction. Now, you might be wondering, why do we have two types of kinetic energy here? Well, the wheel is rotating, which gives it rotational kinetic energy, and the wheel is moving in a straight line, which gives it linear kinetic energy. That's the reason why we have a change in rotational kinetic energy and translational kinetic energy. Now, with all that said, work total is equals to the change in energy, which is the negative change in energy, which is mgh initial minus mgh finals. Now, let's plug that in. Now, the wheel stops, which results to a k final of 0. This means that both translational and rotational energy is equals to 0 because it went to a full stop. That means you can remove 1 half W squared final and 1 half MV squared final, which gives us only negative 1 half MV squared initial and 1 half W squared initial. Kinetic energy in this case includes both translational and rotational energy, as I said, which means that mgh initial minus mgh final is equals to 1 half IW squared final minus 1 half IW squared initial plus 1 half mv squared final minus 1 half mv squared initial plus work done by friction, which turns into negative mgh final because mgh initial, h is equals to 0 at mgh initial because the reference point is the point where it initially fell off. So you have negative mgh finals is equals to negative iw squared initial minus 1 half mv squared initial plus work done by friction. If you derive this, we get height is equals to, how to cope with panic attacks. Height is equals to 1 half IW squared initial minus 1 half MV squared initial plus work done by friction is equals to negative weight, which is mg. So just plug that in. And you get h is equals to 1 half I, which is 12.58 times 27.1 squared, which is rotational velocity which is angular velocity, plus 1 half mass times velocity squared minus 3,506 joules made by friction, over weight. And once you plug that all in, you get the answer, which is 17.8 meters. Now, let's move on to the last question, which is simply, find the magnitude of the angular momentum of the second hand on a clock about an axis through the center of the clock face. The clock hand has a length of 15.0 centimeters and a mass of 6.0 grams. Take the second hand to be a slender rod rotating with constant angular velocity at one end. So first off, you have to convert it into standard units. 15 centimeters and 6 grams should be converted into meters and kilograms respectively. Now, m is equals to 6 grams or 0.006 kilograms, or simply 6 grams over 1000 or 6 kilogram, or 1 kilogram is equals to 1000 grams. Now, length is equals to 15 centimeters, and to make 1 meter, you need 100 centimeters from the word centi. And the radius is 7.5 centimeters, which is simply half the length, because this is a problem about angular momentum, so radius is always needed. So it's 0.075 meters. Now, first, find V and find L, which is angular momentum. Now, take note of the following. This is the second hand. To get the velocity, you need to consider that the second hand makes a rotation every 60 seconds, which means that it gains 2 pi every 60 seconds. Now, convert it into per second and you get 2 pi over 60, which is simply the velocity. Now that you're given angular velocity, you can compute for momentum. Momentum is equals to mv, mass times velocity. So linear momentum is equals to momentum times r, which is simply mvr. So just multiply everything, which is 0.006 times 2 pi over 60 seconds times 0.075 meters, which is, and you'll get the final answer, which is 4.71 times 10 to the power of negative 6 kilogram meters squared per second. Okay, now that that's 3 problem done, please subscribe to my YouTube channel. I might need the help in the future. So yeah, just please do. And this video was sponsored by Mobison. Thank you and good luck.